In this video, I wanted to go over the Arrhenius equation, where we can determine what or we can examine how the rate constant is dependent on the reaction, the temperature of the reaction. Okay, so remember at the beginning of this chapter, of chapter 19, I had drawn this potential energy plot here. This potential energy plot where we have the progress of the reaction as it goes, as it proceeds, right? Is reaction progress, right? Relative to the potential energy of the system. Okay, and you've already had a little bit of practice with drawing out these plots here. So say for an exothermic reaction, right? We have the reactants, some reactant going to some product, okay? The reactants at some initial potential energy, and then the products end up being at a final potential energy, right? And then the difference between those two, of course, is, I don't know why the pen's not working, is our delta H there. Okay, now remember, in order for the reaction to proceed, it has to overcome the activation energy. Okay, so it had this hump here, and then it comes down, the energy falls, and to create the products. And this right here, this height from the reactants to the top of the activation, to the top of this hump, right, is our activation energy. Okay, and up here we have an activated complex or a transition complex, a couple of different names there, and then that was the species that resulted in the two reactants coming together before forming the products, right? And they were at a higher energy because generally those species just have higher energy bonds to where they aren't stable, right? Which is what forms the product in the end. Okay, and remember what I said, temperature does not change the activation energy. It just changes the number of molecules that can overcome the activation energy barrier, okay? And so when we are talking about the Arrhenius equation, we can use the Arrhenius equation to get us to taking into account a couple of different factors. We can come to an overall equation that helps us determine how the rate constant will change relative to the temperature. Okay, now here K is our rate constant, right? K is our rate constant, just like we've been dealing with this whole chapter, little k, okay? E sub A is our activation energy. And then R is our handy gas constant, 8.314 joules per Kelvin mole. And remember, we're going to use this R instead of the 0.08206 because of the joules that are inherent in the units here, right? Because we're dealing with energy. T is our temperature in Kelvin, of course. Okay, and A is what's called the frequency factor. Okay, so this essentially represents how many collisions are happening. So this is just our frequency factor in the equation. So now we can use this equation to relate the rate constant and the activation energy to the temperature of any given reaction. So we can actually rearrange the Arrhenius equation to help us define or to help us determine different rate constants at different temperatures. And then we can also rearrange it to make it such that it follows a y equals mx plus b pattern, to where you can actually solve for the activation energy and the frequency factor given plotting natural log k and 1 over t. All right, so two different rearrangements here. We have one, and this is actually one you're going to be using in lab here, where you're going to plot your natural log of k of your reaction, and you'll find that from the integrated rate laws and such. And you're going to plot natural log of k on your y-axis, okay? And then 1 over t will be on your x-axis. And see, we have this handy y equals mx plus b style of equation here. So then we can, once you plot your data, or the whole class's data, you'll have the slope here, and you can use the slope and the R to solve for what the activation energy of the reaction of bleach taking away the color of the blue dye. We can find out what the activation energy for that reaction is, which is pretty cool. And we can also come up with the frequency factor as well. All right, so that's what you're going to be doing in lab. Now there's another form of this equation that we can use where we can determine the activation energy given the rate constant at 2 different temperatures. Okay, so this is just another rearrangement of the same equation. It's supposed to be little k. K1 over K2 equals the activation energy over R times 1 over T2 minus 1 over T1. Okay, so then if we have 2 different rate constants at 2 different temperatures, we can plug those into this equation and solve for what the activation energy of a particular reaction is. So let's do an example of that now. So here I have some data, some rate constants for a particular first order reaction at 3 different temperatures. Okay, and this was something that was just collected in the lab, right, with some integrated rate laws and such, right? So what you want to do here is you want to take the trials respectively and plugging them into the correct location, right? So you have to be pretty cognizant of your subscripts here for your T2 and T1 and K1 and K2, right? And so we need to put the correct numbers in the correct spots, all right? Or else the negatives won't work out and so on and so forth. So you do this. So if I pick, let's pick trial 1 and trial 2. And you can do any combination of trials here, and it should give you this same activation energy, which is what we're solving for. We're solving for our activation energy. All right, so if you take trial 1 and trial 2 here, and you say the natural log of 2.9 times 10 to the minus 3 over 6.1 times 10 to the minus 2, that's a 2, equals the activation energy, which is what we're solving for, divided by 8.314, okay, joules per Kelvin mole, right? And then we have 1 over, so since our T2 comes first in this part of the equation right here, notice the T2 is first, so we want to make sure that we are using what we called trial 2, right, which is this one right here. Okay, so then we put in our 450. In fact, why don't we just go ahead and put it in the green, right, minus 1 over our trial 1 temperature, right? So that's 400 there. And those are both in Kelvin, units of Kelvin. All right, and then if we just solve for the activation energy, right, we can take the natural log, calculate the natural log of 2.9 times 10 to the minus 3 divided by 6.1 times 10 to the minus 2, which gives me negative, negative 3.04, okay? And so that will be equal to all of this, of course. So now, in order to isolate this term right here, we can divide negative 3.04 by all of this right here. So I would actually just take this entire thing and just move it over to the other side by through division. So if I move all of this over to the other side here, I end up getting 10966 equals the activation energy over R, 314. Okay, and now I also want to point out, when you're putting this into your calculator, I want you to be super careful about maybe even putting parentheses around each of these fractions here so that the calculator doesn't calculate something incorrectly, right? Because you want to do fraction minus fraction, okay? So if you had, so it's 10,966 equals the activation energy over our constant R. Then you just isolate E sub A by multiplying by 8.314, and then you get to 91,172 or 173 joules per mole, right? But since we typically work with kilojoules when it comes to these types of problems, we just convert that bad boy to 91 kilojoules per mole. And this is an easy way that we can use the Arrhenius equation with given the rate constant at two different temperatures, how we can determine what the overall activation energy is for that particular equation or for that particular reaction.